start or wait? So before we start, how many of you have heard of quantum mechanics? Come on, come on. Heard. All of us have heard of quantum mechanics. Okay, good. What have we heard of quantum mechanics? In what context? In modern physics, in some ways, atom is described by quantum mechanics. What else? Sorry? Theory of relativity. Okay. Okay. What else? Tend to unify? Physics of small scale unification with physics of large scale. That we will be able to do today in class itself. Okay. Let's see. So framework theory to apply corrections to small scales. Okay. Corrections which are? Needed in small scales. Corrections are needed in the small scale. Okay. Okay. Fine. So we'll come back to this. Okay. But come in. But okay. Before that, let's go to a philosophical question which we will answer. But let's go back to Newton's laws, something which we know. Okay. All of you, I am sure, know Newton's law, right? What is Newton's law? Rate change of momentum of a particle is equal to sum total of all the forces applied on it, where the vector addition of forces is inbuilt into it, etc. for example, right? Okay. Before Newton's laws, we can write, we have to define where it is valid, right? And that definition comes from the first law, that I define an inertial frame as a frame in which an object stays at rest and continues to be in its state of either rest or of uniform motion unless some forces act on it. If I see an object behaving in such a way, then that frame is inertial frame, and in that frame I can apply all these laws, etc. Okay. Okay. Now, of course, Newton's laws now have position and time inbuilt into it, no? So before even defining Newton's laws, I need to have an idea of position and time, right? And some feeling for what is will be called mass, right? Okay. So before I can even define Newton's laws, I need concepts of or feeling for what I call absolute time. No? Absolute time, it just means that, for example, if I drop this chalk and the time it takes to reach the ground, if I can measure that, and I measure this time in any other reference frame, it will be identical, right? That is all, right? So the other observer may see things differently, but the time of chalk leaving my hand and hitting the ground will be identical in both the frames, absolute time. Similarly, absolute space, right? The distance that the chalk covers on leaving my hand and hitting the ground is identical on all frames, right? Absolute time and absolute space is all frames, even inertial, non-inertial, etc. for example, right? And that's a concept that we need to get to Newton's laws. Is it clear? Okay. Okay. Now suppose I have got to Newton's laws, okay, and I can write, for example, dp by dt is equal to sum total of all forces, let's say, okay, and just to be easy, I can assume conservative forces, and I can write minus okay, so let me write the gradient notation, minus del v, which can in general be a function of x, y and z, right, for conservative forces. Okay. So, from here to here we are assuming conservative. Okay. So, given the background that I have this concepts of absolute space, absolute time, point particle, something which has a mass but no dimensions. Okay. This equation describes the motion of a point particle under the application of certain force. Okay. Now, if I have a single particle, I can uniquely specify its, I would call, state by specifying what? Position and velocity as a function of time. Okay. So, for such a system, I can have a state which can be specified by two coordinates x of t and momentum at t, etc., for example, right. And this is called state of the system. Okay. Okay. So, instead of velocity I have written momentum, because I can have a variable mass problem, for example, right, and Newton's law says rate change of momentum. Okay. But they are roughly identical, mass times velocity is momentum, right. Okay. So, for any given theory to work, I need the regime of its applicability. Only inertial frames this will work. And before I can apply this theory, I even write down this equation. I had a lot of concepts which went in before, which I had to define, for example, absolute space, absolute time, then only I can define d by dt, for example, or d by dx, etc., for example, right. So, the derivative appears in the force, d by dx, d by dt appears. Okay. So, I need a lot of preliminary concepts, then regime of validity, right, and then I can write down the equations of a theory. Okay. Okay. Now, of course, those of you who know some bit of relativity know that this is not entirely the whole story. No. So, other than this being true in inertial frame, we also need, for example, velocities which was much smaller than c for it to be valid. Otherwise, I will have to modify these equations, etc., right, write a relativistic version of these equations. Okay. So, these plus there may be other criteria which define the regime of validity of this theory, Newton's laws, etc., for example, right. Okay. Now, we are going to touch upon a new theory, right, quantum mechanics. So, first question I should ask is, what is the regime of applicability of quantum mechanics? How would I know where to apply quantum mechanics? No? Even before I learn quantum mechanics, where should I apply quantum mechanics? Sorry? So, that is relativistic, special theory of relativity, vagara, right. So, V equal to C, I can have special relativity. Okay. So, some hint was small scales, for example, right, but is small scale sufficient? In physics, if you tell me small scales, I will say it is all bullshit. You tell me small with respect to what, right. Okay. So, small scales would imply what? Around the size of the nucleus. Okay. Sorry, you mean size of the electron? Okay. So, what is the size of the electron? Minus 20. Okay. What is the size of the nucleus roughly? Minus 15. So, from electron to the nucleus is 5 orders of magnitude, right, and from the nucleus to the atom is typically 1 Armstrong, 10 to the power minus 10 is another 5 orders of magnitude, right. So, what you are saying in one breath, quantum mechanics applies to atom, nucleus and electron, no, you are sweeping 10 to the power 20 orders of magnitude, right. Okay. Is there any other criteria? What do you mean? Photoelectric effect is an effect. So, you are saying wherever I see photoelectric effect, I apply quantum mechanics. Okay. So, photoelectric effect is only for photons. So, do I apply quantum mechanics only for photons? Sorry? You can apply quantum mechanics on photons, okay. Okay, you can do that, but photons, yeah, that is fine. Okay. So, we can apply quantum mechanics to photons in some situations. Black body radiation is one, okay, fine. Photoelectric effect can be another one, okay. When a particle, so how would I know when we would show dual nature? No, suppose I throw this pen at you, it has both particle nature and wave nature, right, but it can be very well described by just Newton's laws. So, classical particle and quantum particle, if it is small, then it becomes a quantum particle. Yes, sir. So, small means Armstrong size. Speed will matter. Okay. So, other than size, there may be some other variables also, speed or something, etc. for example, right. Okay. So, this was all teasing. Okay. So, let me define for you, for example, what will define the regime of validity of quantum mechanics. So, you guys have heard of the thing called action, right. Of course, all of us like action movies. Okay. Most of us like probably action movies. We like action in the sense of, jumping, etc. But that is not the action we are talking about, right. So, this is a classical action that Sagar must have defined in the previous classes, right, and we have absolutely no good feeling for it, except that it gives rise to a lot of good things. For example, whole of Newton's laws can be derived from the least action principle, right. So, let me define something called action. Okay. Okay, I am not defining, I am just saying that there is something called action, which roughly has dimensions of energy times time. Okay. 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 Now, suppose I have a system in which I can estimate the rough order of its action, some estimate of its energy and some estimate of the time it takes. Okay. So, for example, in a hydrogen atom, what is the energy of an electron in, let us say, first orbit? Something of the order of electron volt, right? Yes. Let us be very crude. Okay. So, order of magnitude. So, 10 to the power minus 19 in SI units. Okay. So, that is energy. I need time also. So, what is the time scale, let us say, for lack of anything better, that an electron takes to circle around in an orbit? Guess? Sorry? Minus 14 is close. So, let us say 10 to the power minus 15. Okay. So, if you have to estimate, for example, you should roughly remember that the velocity of electron will roughly turn out to be c by 137, okay, and r you know, right. So, then you can easily estimate the time and it will turn out to be 10 to the power minus 15 seconds of the order, Okay. Okay. Then the action is of the order of minus 34, right. And of course, if you know some bit of history of quantum mechanics, quite a bit of it was born to describe the atomic system. No? After Rutherford's experiment, for example, we are trying to come up to terms with the fact that bulk of the atom is nucleus, which is 10 to the power minus 15, and the rest 10 to the power minus 13 is roughly vacuum in which electrons are there. Okay. And if there is a positive charged center, the electrons cannot remain stationary because they will be thrown away, right. The only possibility of having a stable thing like an atom is that they keep going around in circles, right, just like our planetary system. Gravitational attraction will force everything to come to the sun, for example, no? And the sun will in turn go to some center of our Milky Way, for example, right, if everything was not rotating. So likewise for an atom also we had a feeling that everything is rotating, and that is why it is stable, etc., for example, right. Okay. So we did a hand of rough estimate, and we know that action for a electron in hydrogen atom is roughly 10 to the power minus 34 in SI units, right. So joules per second, not per second, joules second or something like that, right. Okay. And that system is definitely quantum mechanical. Okay. So let me prescribe so action I will call S. Okay. So whenever you have a action, a system whose action energy into time I can define S, which is of the order of what is called a Planck's constant. Okay. So extra name h bar, which is equal to 1.34 into 10 to the power minus 34 joules per second, then the system is quantum mechanical. Okay. Implies quantum mechanical, and if the action is 10 to the power 4, 5 orders of magnitude larger, then my system is roughly classical. Okay. Yes.
How much time do we consider for electron to the time period?
Yes.
Take any time to
So that's an extremely good question. So for a system, for example, how do I define what is time we consider, right? So for an electronic system like an atom, a natural time period to consider was one rotation, right? Okay. Now suppose I have a RC circuit, no? That I will never think in terms of quantum mechanics, by the way, right? In RC circuit I would have a natural time constant, for example, right, 1 by root over RC. So that would roughly be the time. And what would be the energy? For a capacitor, what is roughly the energy? So that is the energy, that is the time, right. If that time scale, for example, even in a RC circuit happens to be of the order of action, then all your classical laws will not work. You have to do a quantum mechanical theory of the RC circuit also. Okay. So your charge which is flowing, etc., for example, that you have to write in quantized variables. Okay. And there is a well defined way of doing quantum mechanics of that also. Okay. So is this absolutely clear? What defines quantum mechanical regime is not necessarily the smallness of the system. Particle as big as me can behave quantum mechanically, right, except that I should be able to do things on a time scale such that my action is of the order of 10 to the power minus 34. Okay. So that is the regime of validity. That is one. Okay. Okay. Now generally quantum mechanics we associate with small systems, let us say, because let us think of an electron or an atomic system, etc., for example, right. Now typically, for example, if I want to make a measurement, suppose I want to see a particle, for example, right, I shine light on it, the light that is reflected from it I see, no? and typically the mass of the system is so large that light does not change the momentum of the system, right. But if a particle is very small like an electron for example, etc., doing an act of measurement on it can change its momentum or even position. I shine light on it, light will just shift it slightly, no. And I have as of now no way of figuring out distances smaller than 10 to the power minus 10, right. So, if light shifted it by 10 to the power minus 13, I would not know, right. Okay. So, what I am implying is a experimental uncertainty in the measurement of position and momentum of a particle. Okay. That should for example imply that it will not make sense to talk of a position of a particle in quantum mechanics, roughly, just to motivate. I am cheating here, but just to motivate. Okay. And similarly, it will not make sense to talk of the momentum of the particle, right, right. Okay. Now, that is in conflict with our way of thinking, where our state of the system we need to define in terms of x and p, right. So, I need a new way to describe the state of the system. Okay. So, that of course is the need of the hour. So, one new description of state, right, and second, so new description of state will have certain constraints on it, right, so that we remain in the quantum mechanics regime, etc., for example. Just like here for example, the momentum cannot be greater than a certain quantity, otherwise it becomes relativistic, etc., for example, right. So, that will be one. Once I have the state, I need an equation of motion to describe the dynamics of that state, no, just like Newton's second law, right. I will need an equation of motion for the state. Okay. So, equation of motion so this is true in any theory in general. Any theory I construct, I will always need something to describe the state, an equation of motion for the state. Okay. And then I need a prescription to relate the state to some physical observables. No? Suppose I do some measurement, right? State to observables, whatever experiments I will do. So, this should be a trait for any theory, any new theory roughly. Regime of validity, something to describe the state of the system, then some equation of motion which governs the dynamics of the state, and of course, in general the state can be very abstract. So, I should have a prescription to convert it into something which can be experimentally measurable, right, of course. Now, I can write hundreds and thousands of theories like this which will satisfy this criteria, etc., right. For example, I could have written variants of Newton's law, dp by dt is proportional to the derivative of the force, right, double derivative of the force, etc., for example, but not all of them will survive the test of experiments, right. So, the theories which are long lasting stay because they survive the test of experiments, right. Today also I can write down a new version of quantum mechanics. I do not believe anything that these guys did, etc., for example, in 1925 to 30, and I am a genius, I will write down my own version of quantum mechanics, right. But it has to survive the test of all the experiments that has been done. No? It should be able to predict and tell you all the stories, right. So, it is pretty useless, Right? It's an idea. It's not a theory. It can be even a crazy idea. Right? Okay. So now let's just jump into quantum mechanics, okay, without going into historical perspective, etc. We will come to the motivation later, after having seen some bit of quantum mechanics. Okay. Okay. So let me say that there is something which I can write down a notation. Okay. So state of the system. I will write down this notation psi, which can be a function of x and t in general, right? Okay. And there is a name which has been given to it in the literature. We can call it anything, but just to be consistent with books, we will call it wave function. Okay. And wave function has some historical meaning. Okay. Light, of course, behave like waves, right, in most cases, diffraction, interference, right, but in some cases it does behave like particles, no? Photoelectric effect, Compton effect. To describe Planck's theory, for example, of black body radiation, we need a discrete nature of light, etc., for example, right. So by the way, do you know that Newton also had a theory of light, which is called corpuscular theory of light, which is identical to this new notion of light being a particle, right. But at that time we could not do these experiments, for example, with those technologies to confirm this behavior, right, and diffraction, etc., for example, we had a very hard time explaining with corpuscular theory of light. So even though that theory also was given by Newton, equally bright guy who gave the Newton's law, right, because it's the same guy, but that was discarded because it did not stand the scrutiny of experiments, right. The idea was nice for some time, etc., but then slowly it died, right. Now we don't read it in the textbooks. Okay. So any theory has to survive the test of experiments. Okay. Okay. So light, of course, behaves, sometimes it will decide to behave like waves, sometimes it will decide to behave like particles, right. Okay. Then similarly, we will see that electrons, being particles, can also sometimes decide to behave like particles and can sometimes decide to behave like waves. Okay. And this is somehow inbuilt, and that is why the name wave function. Okay. Okay. So historically, for example, there are a lot of developments to explain this Rutherford model of the atom. For example, Bohr came up with this idea that the radius of the electronic orbit has to be some multiples of this wavelength of the electron, which de Broglie prescribed, for example, etc., right. So there was some lot of ideas floating around which suggested that electron is a wave. So de Broglie wavelength of the electron, for example, was one. Bohr's idea of 2 pi r is equal to n times lambda was another one. Then another idea associated with waves is what is called the uncertainty. Okay. So in the sense of following, so suppose I take a string and I create waves on it by striking it, right. Okay. Now suppose I have a very regular looking wave, lot of ups and downs, etc., for example. I can specify the wavelength of the wave, right. What about the position? I have a nice wave, I can specify the position or not. The wave is everywhere, no? So I cannot really specify its position with great accuracy, right? But I can definitely specify its wavelength. And this wave I created by keeping doing this, no? I hold this end and I keep doing this, right? So nice description of lambda or momentum. Wavelength is related to momentum, right? Inversely, okay? But no accurate description of position. Okay. Now I can generate another wave. I will just take the string and do this once, right? So I will get a wave which will have one up which is traveling, and here I can specify the position of the wave accurately wherever this hump is, right? So position well defined, lambda naught or momentum naught. So this is another interesting property associated with waves. If I know the momentum of the wave, I do not know its position with great accuracy, right? If the momentum is unique, then the wave is roughly all over the place. So x I cannot specify, okay? And if I know the position of the wave, if the wave has only one up, then I cannot specify its momentum with great accuracy, right? Because I do not get a concept of wavelength, because I need two troughs to define a wavelength, etc., for example, right? Okay. So this is a physical idea, and this can be put on a very firm mathematical footing in the sense of Fourier transforms, etc. Okay. And wave theory, any wave theory has a lot of uncertainty built in terms of the uncertainty in the measurement of the position and the uncertainty in the measurement of the momentum. Okay. So any wave theory, for example, will prescribe that the product uncertainty in the measurement of delta x and uncertainty in the measurement of delta p is generally larger than equal to some number. And this is true for any wave theory. Okay. Okay. And this is not like our particle nature. In Newton's mechanics, I know the position and the momentum very accurately. If you tell me the momentum now, position now, and all the forces on it, I know how to calculate it at all times, right? But in waves, even at a given time, I cannot know the position and the momentum with great accuracy, right? And quantum mechanics was built to take care of this, no? Wave nature of electrons in some sense, right? So I have to give up on my ideas of position and momentum being accurate, right? That is why we need to define a new variable to define the state. There is uncertainty in the position, there is uncertainty in the momentum, I cannot use them as state variables. No? Is that clear? So I need a new paradigm, something new to define the state. Okay. Now that something new is wave function, this is number one requirement. Okay. Now this wave function needs to have a dynamical equation of motion. So let me write down the equation of motion. Okay. So the equation of motion goes like this. So I h cross So, I h cross time derivative of the state vector is equal to minus h square by 2m, this guy plus this guy. Sorry, dou x2, sorry. So, this is in one dimension. Okay. So, I typically use a shorthand notation for these guys. So, I just write this as this generally, okay, and this I generally write as dou x2. In that way, I can write it in one line only generally, no? Okay. So, this partial derivative acts on this guy twice. V is typically the potential energy, similar to what we would think in our classical mechanics, okay. And this is the equation which describes the dynamics, okay. So, this is called the Schrodinger equation. Okay. So, now historically when quantum mechanics was being developed, right, a lot of the initial ideas people were discovering or discussing wave properties of electrons, okay. Like we just described this uncertainty principle, for example, right. So, Heisenberg came up with the uncertainty principle for the electron before even Schrodinger equation was written down, okay. Then Niels Bohr, for example, came up with the idea that electrons in a nucleus, for example, orbiting around a nucleus need to satisfy 2 pi r is equal to n times lambda, no, but lambda is associated with a wave even before this equation was written down, okay. And de Broglie, even before all of them, had, for example, this, that particle can behave like wave, and this is the wavelength in terms of momentum, right. So, all of this discussion going on, we are able to explain a lot of things, etc., for example, and Debye made a statement that everybody is talking about wave nature of electrons, but nobody is writing down a wave equation. So, unless you write down a wave equation, I will not believe any of this crap, something to that extent, okay. And then basically this is the wave equation which Schrodinger wrote down, okay. So, this describes the dynamics of the system, etc., for example, okay. Now, we need to ask what is the meaning of this wave function, what does it represent? No? It is a very abstract concept, it is given by a complex differential equation, right, homogeneous, first order in time, second order in space, and so on, okay. Okay. So, we need a way to interpret this psi and connect it to physical observables, right. Okay. So, let me make again just hit you with the result, okay. So, let me say that the psi in general can be a complex quantity, and complex quantity I can't relate to any realistic observable, etc. So, what I can define is this quantity which is mod psi square, okay, at a given location, let us say, and time, and this defines the probability of finding a particle at a given x and t. Okay. So, note that we are being consistent with whatever we have said till now. We are trying to write down a wave theory for electrons, number 1, right. Okay. Wave theory implies uncertainty by default, no, I cannot know the position and the momentum both together, right. So, whatever my state variable be, that better be undeterministic, unprecise, etc., for example, right? And then it makes sense for it to have a probabilistic interpretation, right? So, this just measures the probability of finding a particle at a given position. Okay. So, this is slightly imprecise statement, you can make it more precise. By saying that if I integrate this probability let us say one dimensional from A to B, then this is equal to probability of finding particle P at a time t in the interval AB, okay, both inclusive. That is my precise interpretation of the wave function. Okay. There is a name given to this interpretation, it is called Copenhagen interpretation, popularized by Max Born, Niels Bohr, etc., etc. Okay. You can also come up with a different interpretation of the wave function. Okay. But this works, let us say, okay. This probabilistic interpretation works and is probably the most well understood, etc., for example, well understood in the sense of most taught, let us say. Okay. 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 Yes. Question? Okay. Now, since psi I am associating with the probability, it better satisfy some criteria. No? Probability of any event cannot be greater than 1, for example. No? So, if this A and B I can extend to infinity, then I have covered the whole one dimensional universe and the particle better be there, if there is a particle at all, right. So, that implies that this has to be satisfied. No? This is the criteria or my state wave vector, right. All functions like this, for example, which satisfy this criteria are called square integrable. Okay. That is the name given to functions like this. And any physically relevant wave function has to be a square integrable function, period. Okay. Okay. Now, you should immediately ask me, for example, what guarantees this? Meaning, I have a state equation plus an external condition, what guarantees this? No? Okay. To answer that, there is a homogeneous equation. I can multiply psi by any constant and the equation will still be valid, right. Constants will just cancel out everywhere. No? So, because my state equation is homogeneous, I have this flexibility to normalize my wave function by any constant, and a constant has to be always chosen such that the normalization is 1. Only then I can have a probabilistic interpretation of the wave function. Agreed? No? Okay. This is 1. Okay. Generally, for example, what would I expect for the wave function to be at infinity? Constant? If it is a constant at infinity, can it be square integrable? So, okay, let's make it easy. Huh? Okay, so let me get rid of this. So, let us think this as the area integral. So, mod psi square has to be always positive, and this integral is the area under this curve. Right? If this guy is going to a constant at infinity, the area is going to infinity, diverging, right? So, mod psi square better go to 0 as x goes to infinity. Okay. Okay. I can even extend this and say, let me set my wave function to 0. So, mod psi square is the real part of the wave function plus imaginary part squared. And since the sum of these two are going to 0, let me say the real part of the wave function goes to 0 and the imaginary part of the wave function goes to 0. Right? Since mod psi square is the sum of two terms, each of them goes to 0. Right? So, I may even say that my psi goes to 0. So, this 0 is a complex 0, 0 real plus I 0 at this. Okay. So, these are the two criteria that the wave function must satisfy for it to have a probabilistic interpretation. We are on the same page, right? Okay. So, the properties that we want in the wave function square integrable, or normalized to 1, vanishing at plus minus infinity, right. Now, of course, you can tell me that there is a wave function, for example, psi is equal to 1 everywhere. No, that is not a square integrable function. So, that cannot be a valid function, that cannot be a valid wave function, right. So, the space of total functions is much larger space than the space of allowed wave functions, okay. Or even the trivial case, psi can be 0 everywhere, but psi is equal to 0 everywhere implies that there is no particle anywhere, right. So, that is a trivial wave function which is also not allowed. Likewise, I can construct a lot of examples. Okay. So, only the domain of square integrable functions can give rise to a physically valid wave function. Clear? Okay. Now, you must ask me about measurement. Suppose there is a quantum mechanical particle, the state describes it, its equation of motion is given by the Schrodinger equation. If I do measurement, what does it mean? Right? Okay. Okay. So, before that question, so let me ask you, so let me make it monotonic to make it easier. Suppose I have a wave function like this and I have a A1 B1 interval here, and I have a A2 B2 interval here, such that this is equal to this, no? And let us say the probability of finding the particle here is 1, and the probability of finding the particle here is P2. So, which one is larger, P1 or P2? P1. All of us agree? P2 is larger or P1? Yeah, my friend at the back there. So, the distance. So, this distance otherwise you cannot say. Sorry? Okay, so let me just say that B1 minus A1 is equal to B2 minus A2. Then the question is valid, otherwise the question has ambiguity. So, my friend there, I will ask again, okay. What is the answer? Sure? Okay. Which one is larger? P1, P2? My friends at the back here. P1 ज़्यादा है या P2? P2. I am for P2. P2? Why? So, why is P2 larger? See, the probability is just the area under this curve. So, this area is larger, let us call it A1, or this area is larger. Which area is larger? A1 is larger? Okay. Then A1 is equal to P1, right? This is the mod psi square. Between some A and B. This is the probability of finding the particle between A and B, right? And this A2 is just P2. So, which one is larger? If I do a measurement, where are you likely to find the particle? P1, right? Okay. Are you 100% sure that you will find the particle in? No, right? Because it is a probabilistic interpretation. There is a more probability of finding the particle in this interval than in that interval. If I do actual measurement, I may not find the particle anywhere between these intervals. I may find it somewhere else completely. Okay. Okay. So, now I want to briefly discuss what is the meaning of measurement. Okay. So, suppose I have one electronic system, okay, and I do a measurement, and suppose I do a measurement for the position of the particle. I have devised my experiment such that I will test only x, location of the particle. So, one experiment, one particle, will I measure some x or not? We can design some experiment, let us say, okay. But suppose I could design such an experiment, will I measure a definite x or not? Sorry? No, there is a probabilistic interpretation, etc., fine. So, recall statistics. How does statistics come about? I do hundreds of experiments. Based on hundreds of experiments, I get a distribution. But suppose I do one experiment. Suppose I am measuring the gravitational constant by just measuring how long a pendulum takes to swing. All of us must have done this in a school, no? So, in one experiment, will I get a definite answer for G or not? No, one answer will definitely give me a definite value of G. Correct or not, I do not know. But it will give me a precise answer, right? So, likewise, if I do an experiment here also I will get one precise answer for x. Okay. Now, suppose I do a different experiment, same particle, I prepare it in the same state, and I again do the same measurement. Will the previous x and this x be same? How many? Definitely yes. May vary a little, okay. Why not much? So, second measurement, what will I see? May vary, sure. My friends at the back, may vary. Why? Because you believe that, or because he is smart and he answered that? You believe, okay. May vary or same? Sorry? So, momentum I am not worried about right now, I am just doing a x measurement. Will I get the same answer or not? Maybe vary, okay. So, it is just like any statistical interpretation. I do G measurement 10 times, I may get slightly different answers, third figure, fourth figure, I do not know, depending on the sensitivity of the experiment. And then if I collate all these experiments, for example, I will get a statistical average, statistical deviation, right. But then I have done the experiment 100 times, right. So, what I have done is taken what is called an ensemble average. I had prepared the system in the same state. For the pendulum experiment, I had a marked angle, I take it to the same angle, right. So, I prepared it in the same state, did a measurement and measure the variations in the value reported, right. So, likewise here also, if I prepare a quantum mechanical system in the same state psi and do hundreds, thousands of experiment, I will record different values of any observable x, p, I can measure energy, I can measure angular momentum, linear momentum, anything, right. I will get set of values and they will have a distribution, okay. From the distribution I can extract the probability distribution, right, and that probability distribution is this psi, mod psi square. So, is that connection clear? Okay. Okay. Now, if I have one ensemble and I do a measurement, I will definitely find a particle at some place, right, but that I may not be able to predict from here. It will give me some probability of finding, probability distribution of finding at x, etc., for example, right, some expectation value, but the actual answer may vary from this expectation value. So, the actual answer will collapse to this expectation value when I do a ensemble averaging. I do thousands of experiments and then I take a standard deviation mean of that, the mean will agree with that, right. That is the uncertainty in quantum mechanics. Okay. Okay. Now, let me ask you another question. Okay. Suppose I do a measurement of a particle and I find that the particle is at some location C. Okay. Can I tell you where the particle was just before that measurement? You have the equation of motion. So, okay. So, let me just say that it is a very, very tough question. Okay. Philosophically, there are three ways to answer this. Okay. I can be Einstein and say I am a realist. Since at time t I measured that the particle was at C, at time t minus epsilon also the particle was at C. Makes sense, no? So, this is Einstein's answer to this question. Okay. Okay. Now I can be Niels Bohr or Max Born, for example, and I will answer that the particle could have been anywhere. I really do not know. Okay. So, this is the answer which can be called old school, no, or Copenhagen interpretation answer. Okay. Since I did not make a measurement, the particle could have been anywhere. Okay. And then I can be Pauli and say that I will refuse to answer this question. It does not make sense to ask a question to which I cannot have a confirmed answer. Since I did an experiment at time t and I found the particle at x, I did not do a time at experiment at t minus epsilon. There is no point in asking this question. This question is as good as asking, for example, how many angels can sit on a pin of a needle. He actually said that. Huh? So, it is as useless a question as that. Okay. And that is the problem with quantum mechanics, initial days roughly, okay, with this philosophical interpretation. Okay. Which of these three is correct, for example, right? Okay. So, now of course, we know the definite answer to this question. Okay. So, the third answer is most wrong. Okay. You can always ask a question, it is always good to ask a question, etc. Okay. And now, because of work of Bell, etc., we know that the second answer is correct. We cannot really say where the particle was. Okay. And that, by the way, is also related to your this Schrodinger's cat problem, if you have heard about it, etc., for example. Okay. Okay. So, fine. Let us revise. Okay. So, to describe the state of the system, we need a state variable x, p or psi in quantum mechanics. Okay. Quantum mechanics comes when my action of the problem is of the order of h bar, which is 10 to the power minus 34 roughly joules per second, sorry, not per second. Okay. Okay. Then somebody wrote down an equation for the state variable, okay, which could have been incorrect, but we know it to be correct because it satisfies lot of limits, and we have not been able to come up with any experiment which disproves it. So, unless there is something better, I will believe in it, and that is your Schrodinger equation. Okay. So, it is as good as Newton's equation. I could also choose to not believe in Newton's equation, but I know it works, and that is why I believe in it. That is likewise Schrodinger equation works, so I have to believe in it given certain limits. Okay. One of the limit was of course that the action is this, etc., for example. Then the Schrodinger equation that I wrote down, etc., is called the non-relativistic wave equation for the electron. It also works when the electron velocities are away from the relativistic velocities. Okay. So, it works in atoms because the velocity of electron in an atom is 1 by 137 of the velocity of light, right. So, that is 2 orders of magnitude, right. So, you know relativistic corrections are of the order of v by c whole square. That would imply relativistic corrections are of the order of 10 to the power minus 4 to any quantity that you can calculate. So, we can for the time being forget about them. Okay. There is of course a wave equation which works in that regime also, that is the Dirac equation. Okay. That is story for later. Okay. Now, the wave function, because it describes a wave nature of the electron, has a lot of uncertainties built into it. So, the best we can do is possibly have a statistical interpretation of the wave function. It defines the probability distribution of possibly finding a particle at a given location. Okay. Since it is a probability distribution, it better have these properties that it is normalizable or square integrable, otherwise it will not be a probability distribution. No, sum of all probabilities have to add up to 1. Okay. And since we have a continuous wave equation, it must vanish at the boundaries plus minus infinity, etc., for example, right, otherwise it cannot be square integrable. Okay. among all the possible functions, only the functions which satisfy these two criteria can possibly be wave functions of a particle. Okay. And Schrodinger equation being a homogeneous equation, etc., it allows us to normalize the equation, etc. Okay. Okay. So this is step 1. Okay. Now step 2, for example. Okay. So let me ask you this question. This is a homework question. Okay. Suppose I normalize the wave function at some time t is equal to 0. Okay. What guarantees that it will stay normalized as I evolve the system? So this we agree, right? The wave function has to be normalizable at all times. All times? At any given time it is a probability distribution, right? It has to remain normalized. But then the normalization should not change with the dynamics, no? Otherwise every time I have to normalize, come on, I mean that's too much of work, right? And it changes the interpretation completely. So once if I normalize the wave function, it should stay normalized, right? Can you show this? So if I had to show this, for example, all I am asking is that I have a condition that psi star, which is mod of psi square, is equal to 1. All I am asking, can we show that d by dt of no? So the way I would go around, I would take and d psi by dt I can write in terms of my wave equation, right? I can replace by the double derivative, etc. And then maybe I am able to do some integrals, either directly or by parts, and maybe use some conditions that the wave function vanishes at 0, etc., for example. No? So this you should be able to prove. This is a homework to prove this, right? Otherwise it will not make sense, any of what we have said. The normalization condition cannot change with time. Okay. Okay. Now suppose I want to measure the position of the particle, right? So all we have said about the state, probability distribution, etc., we have not defined a physical observable, which is the third step. No, we need to relate the state to the physical observable. So suppose I want to measure the location of the particle. X so I'll have to define something like the variable times the probability distribution function and if I do this, so I have a variable, the probability of finding this at this, and I am summing over all of these probabilities. I will get the expectation value of the particle, right, position. This is the only observable I can define in quantum mechanics, which is statistical expectation value. Or what I call ensemble average. Purely in a probabilistic sense. If I do thousands of experiments, I measure x1, x2, x3, x thousand, I do averaging with this probability distribution, this is what I expect to find, right? Okay. It's fine? Okay. Now with this x, I will also have a classical mechanics concept of velocity or momentum, right? So can I define something like dx by dt, which would have some semblance to classical velocity? No? So this x in symbol average is like the classical position of the particle, right? Newtonian mechanics is fully deterministic, so I do one measurement or 1000 measurement, x is unique. Quantum mechanics is wave nature, undeterministic, statistical interpretation, so I need to do a lot of measurements and I can only talk about ensemble averages, right? So now what is the velocity of this ensemble average? Right? I can define, so I can again work with this. I can take the time derivative inside dx by dt psi star, so there will be lot of terms etc. d psi by dt again I can replace etc. for example by the Schrodinger equation, do lot of tricks etc. for example. And if I try to calculate this quantity, okay, so let me just write down the final answer. Okay, so this will turn out to be psi star minus psi h by m dx psi dx, and all the psi's are functions of x and t etc. Okay. So what I am saying is I take the time derivative of this equation. So there are three terms. So by chain rule I'll have a lot of terms, right? Once derivative of this, then derivative of this etc. Derivative of this I can transfer to the derivative of the wave functions by doing integration by parts. Okay. And these limits are minus infinity to infinity, right? When I do integration by parts, I'll have some functions which will have boundaries, right, to be evaluated at plus infinity and minus infinity, and I know the wave functions go to 0 at plus infinity and minus infinity. I use all these conditions etc., do some mathematics, and if I do this I'll arrive at this answer. Okay. This is del xi by dx. So this operator has to always act on the whatever is on the right. Okay. Sorry, so I use the word operator, so this derivative. Okay. So this I have not done explicitly, but this you can show. Okay. Okay. So now if I multiply this side by m etc. for example, if I bring my m this side, get rid of m here, then this should just be the expectation value of the momentum. No? Okay. And expectation value of momentum I would think in terms of psi star. There should be some momentum here and psi, right, and that would give me the expectation value of the momentum. So this I can think in terms of let me call this p hat. Okay. Just because momentum doesn't have a definite meaning, right, I'll call it a hat. Okay. Expectation value of the momentum has a meaning etc. And this guy also I can write in terms of psi star x psi, so that this and this are written in the same format. Okay. I have not done any trick as of now. Okay. And this x also I can call hat. Okay. So hat I have just used to define in quantum mechanics what we will in general call operators. I did nothing. So I am just saying this is expectation value of the momentum, right? Okay. Naively, I would think expectation value of the momentum as the probability distribution times momentum variable integrated, right? So in this case, it turns out if I do this calculation, this is the momentum variable, right? The momentum variable, since it turns out to be a derivative etc., for example, which has to act on this wave function, let me call it an operator, right? And just to distinguish a variable classically from a quantum mechanical variable, which I call operator, it acts on something, I have given it a name hat. Okay. So classical variables in quantum mechanics go to what is called operators. Okay. So for example, here I can have a x p generally classically, quantum mechanically we generally call them x hat, p hat, etc. Okay. Now quantum mechanically x hat is just x, p hat turns out to be minus I h cut delta x, and this comes out of this calculation. Is that clear? Okay. And since this is not a variable in a classical sense, that I cannot change its orientation, I cannot put it here, then it would be acting on psi star, right? I have to place it here such that it acts on psi. So this is not a classical variable in some sense, so I will call it an operator. Okay. An operator is something which, for these lectures, something which will act on the right to it. So there can be operators like x, for example, which just multiply something to the right on it, but multiplication is the same, I change the position also, nothing will change. But then I will have operators like which are derivatives, double derivatives, third derivatives, etc. Their position I cannot change, right? And that is why I will call them operators. Definite position, they act to something which is on the right of it. Okay? Okay. Yes.
Can they act on psi star? Can we interchange the position?
You can interchange the position, okay, but then the operator will also change. Okay, so this, by doing partial integration, I can of course write in a different format, right? Okay. But if you are just to be consistent, for example, that psi is the wave function, psi star is the complex conjugate, psi is defined by that equation, etc., for example, then this is one consistent way of writing it. I can write it another consistent way, for example, I can define psi star as the wave function, and then I can change the notation, etc., for example, plus I will become minus I, etc., etc. That would also be perfectly fine. Okay? But this is one consistent way of doing it. Okay? Okay. Now, in classical mechanics, all my whatever I could measure, position, momentum, what else? Kinetic energy, what else? Angular momentum, linear momentum, anything, no? So any observable or measurable quantity in classical is generally a function of x and p, right? Okay. And similar, so for example, L, R cross P, no? Okay. So anything is a function of R, position, and momentum. Likewise, any quantum mechanical operator also I can construct in terms of these two fundamental operators. I will measure kinetic energy, I will measure potential energy maybe, potential energy is a function of x generally, right, or let us say angular momentum or anything. Okay. So, any operator q that I can have, classical variable. So, this is all in classical mechanics, will translate to here as an operator q. So, this was a function of r and p in general. Here it will become a function of r hat and p hat, where p hat is this operator. So, this p hat is specifically for one dimension, but I can generalize it to 2-3 dimensions, IH dou x with the I component plus IH dou y with the y component and so on. Okay. And this is the relation. Okay. And this I can explicitly show by doing calculations of this kind. Any operator, whatever is the classical variable, I can find a corresponding quantum mechanical operator. Okay. Just to give you an example, so since we have internalized these things, let me get rid of this. So, for example, I can try to calculate the kinetic energy. Let us say T in classical mechanics is just p square by 2m, right. That in quantum mechanics should become a observable operator T hat, which will have similar form 1 by 2m times p square. So, minus IH del x times IH del x, no, and this guy acts on this and this guy acts on whatever is to the right, right. So, this is nothing but minus I gives me 1, so h square by 2m dou x 2, right. So, if I have to calculate the, so there is a minus I and a I, sorry, there is no p star. So, this is p into p, p dot p, right, yeah. So, p star we do not need, p square is p dot p, 2 times p, it is not a mod square. So, in operators, for example, see, okay. So, operator can be complex, that is fine, okay, but by operator by itself does not have any meaning. Okay. So, the meaning will come when I sandwich it into between psi and psi star, and that is what is guaranteed to produce a real answer. Okay. So, in writing p square, I do not need to do p star, never, p time, oh sorry, minus, yeah, then there is a minus, sure, that is my mistake. Okay. It is not p star, please. No, there is a minus I, so I square gives you minus 1, right. Okay. So, then if I have to calculate the expectation value of T, then this is just psi star minus h square by 2m dx. Okay. Okay. And likewise for any operator. Okay. Okay. Now that since our time is up, okay, let me just come back to one final repetition point. Okay. So, our Schrodinger equation, if you remember, it was minus IH dot T of psi is equal to minus h square by 2m dot 2x of psi plus v psi, no? And this operator you already see is the kinetic energy operator, right? And this operator is the potential energy operator. So this looks like a total energy, and total energy in some different formulation in classical mechanics we call the Hamiltonian of the system, right? So the left hand side should generally be some conserved quantity which is the total energy of the system, no? And dimensionally is it consistent? I have a h bar and d by dt here. So h bar is energy into time and dt time is below, so it is dimensions of energy, right? So that is your Schrodinger equation in some sense. Yeah. So what I am trying to say is, you know, wave equation for light, it is second order in time derivative, right? Dou 2 E by dou T2 is equal to some constant times dou 2 E by dou x2 in 1D. Why don't I have that equation for the electrons? Because for the electrons the kinetic energy is not P times C, it is P square by 2m if I have to make a classical connection, right? And that connection I cannot break, because suppose I have a theory quantum mechanical action etc., but action can gradually increase to bring me to the quantum mechanical regime, right? And my quantum mechanics should be able to bring me to classical mechanics in that regime, right? Because it is a theory which can lead to Newtonian mechanics, let us say. It is a theory which is for smaller action times. Newtonian mechanics is a theory which is for larger action times. So if I take a smaller action time theory and do it for larger action times, I should be able to come to classical mechanics, no? And operator correspondence guarantees that, no? This is deeply related to what is called Ehrenfest theorem, okay? So whatever operator I define, that is a classical analog, okay? So if my theory becomes such that my action starts getting larger, you will see that I can do averaging of that theory and reproduce just Newton's laws or Hamilton's equation of motion, if you like. That is another way of writing Newton's laws. That was done in the last class, I think, right? Sagar did it. Okay. So that is all I wanted to say for today. Okay. So will you go back and read, or it's just too exhausting? Okay. So books, right? Quantum mechanics, if you want to read, there is a very nice book by Griffiths, the same Griffiths who wrote that electromagnetic theory. Okay. Thin book. When I was a student, thin books were my favorite. So thin book, easy to read, very good, very cheap, so you can buy. Okay. No point in downloading and taking a printout, very lousy. Okay. 300 rupees something. Or there is another book by Gasiorovich, again thin book with lot of appendix materials available on the site of the Whaley. So quantum physics, either introduction to quantum physics or basic quantum physics, something like that, Gasiorovich. I will bring both these books in the next class. Again cheap, 300 rupees or something like that. Okay. So most of the discussion that we did today is in Griffith's, I think, first chapter, yeah, or Gasiorovich second, third chapter. Okay. Any questions? No questions? Right. So good question. So why do we use complex numbers in quantum mechanics, right? Okay. I didn't choose it. We didn't choose it in the sense. Okay. What came out naturally was the Schrodinger equation. Now that of course allows complex solutions, which are square integrable and which go to 0 as infinity. So they are in principle allowed. Okay. And several situations we will find that the wave function is just complex. You cannot do anything about it. In many situations, we can actually choose a real valued wave function, but in some situations, you have to choose complex. So the question you should ask is, any observable that I calculate, this has to be a real number. My wave function can live in any space. I mean, it can be complex or it can be even more complicated object, right? It can be a vector, it can be anything else also. It has interpretation in the sense that wave function squared psi star mod denotes the probability of finding a particle at a given location. So it's a probability distribution. But the probability distribution is the mod squared of the wave function. So wave function can still be complex, and mod squared quantity has to be real. Right? More questions? Which one? It looks like the Hamiltonian. It is actually called the Hamiltonian, etc. For example. So this is just to show you an analogy, nothing else. Okay. So yeah. Okay. So okay. So let me just finish the point. Okay. I'll just take 1 minute. So classically, my Hamiltonian is what? P square by 2m plus v. Let me take conservative forces only x, etc. for example. Okay. Okay. And correspondingly, I can define a quantum mechanical Hamiltonian, right? Where my p becomes p operator minus IH dou x square by 2m, okay, plus v of x hat, right? Now classical mechanics way we can write down the Hamiltonian equation of motion. So I have a p and a x, so dou h by dou x is equal to something and dou h by dou. Which one is which now? You have to tell me. So dou h by dou x is p dot plus or minus? Okay, then this guy has to be minus. Sure. Sure. I will put the minus sign here. Okay. So the easy way, so the only way I remember this, for example, is think of harmonic oscillator immediately, no? 1D harmonic oscillator. See, this equation will give me the force, which would be minus times the momentum, right? Only when then I'll have equilibrium. Okay. And this is just the definition, x dot is v or momentum in some sense, right? Yeah. Okay. Now I take a quantum mechanical, for example, variant of this problem. I calculate the expectation value of h operator, etc. for example, right? So I can calculate the expectation value of h quantum mechanical, etc. And these equations will still be satisfied. So this will give me, for example, expectation value of the Hamiltonian operator is equal to minus p dot and expectation value of dou h hat by dou p, okay, which will give you x dot expectation value. So that's the correspondence. So it's called Ehrenfest theorem. If you like, you can show for a lot of variables, etc. But classically, whatever I had the equation of motion, quantum mechanically I can just reduce them to the equation of motion for the expectation values, period. And this has to be there, no? Because ultimately I am describing a particle which can go from quantum mechanical regime to classical regime, and my quantum mechanics should be able to capture this transition, period. Right? Okay. So next class you should have a lot of questions, because this is the first time you have been hit with quantum mechanics. So you should have a lot of psychological issues. If you are not having, then you are not appreciating the lecture. Okay? Yeah. So V is a function of x, which is an operator. So V is also an operator. Okay, I can write V hat here equally well. So V is generally x, which is an operator. Okay. So now question. Okay. Yes. So before that, let me ask the question. Okay. So Hamiltonian equation of motion, is it valid only for conservative systems? It is valid in general, right? So in the potential energy, I can also have other terms, momentum dependent terms, right? Okay. So here also in the quantum mechanical potential energy, I can have momentum dependent terms, and it becomes a more complicated operator. Yes, sorry, last question. Hmm. Hmm. No, but you are trying to find a position of what? That point? Then you already know the position. You are trying to find the position of the wave. So position of the wave will have only meaning when wave is localized. When wave is spread, then position of the wave has no meaning. Okay. So suppose I do this experiment. So I understand. See, what you are saying is, suppose I mark a point, right? I can figure out what is the amplitude of the wave at that point. But there will be a different amplitude at a different point. How does amplitude correspond to location of the wave? They are completely different things, right? I cannot specify the location of the wave. Okay. So Griffiths and Gasiorowicz. Okay. Yes. We have not defined. So T plus V will always make sense whether conservative or not conservative for energy, right? The whole point is whether energy is conserved or not, right? Then it will not make sense to write in this form equation of motion, etc. Okay. Now quantum mechanically, when you are at small domains, etc., most of the forces are conservative. Okay. Let me make an even bolder statement. Most of the fundamental forces in nature are conservative. There are 4 fundamental forces: electromagnetic theory, gravitation, weak interaction, strong interaction. All of them are conservative. Non-conservative forces are generally arise when we look at macroscopic picture, friction, etc. For example. Right? So quantum mechanically, most of the forces are conservative. Okay. If they are not, then most of this formulation may not work. Okay. Okay. So more for tomorrow.